In Notes 2.4, we're going to be talking about the combined gas law. The combined gas law is the last of the gas laws in which you will be responsible for knowing. Okay, up until this point, we've talked about Boyle's law, which relates the relationship or deals with the relationship between the pressure of a gas and the volume of the gas. And an equation form looks like this: P1V1 equals P2V2. And we've talked about Charles' law, the relationship between the volume and the Kelvin temperature of a gas. And in equation form, we know Charles' law is equal to V1 over T1 equals V2 over T2. In both Boyle's and Charles' law, there are some assumptions that we need to make. When talking about Boyle's law, we assume that the amount of gas that we are working with stays constant, along with the temperature. When talking about Charles' law, we assume the pressure of the gas remains constant, along with the number of the particles. But what if that isn't the case? What if we are dealing with a situation where both the pressure, volume, and temperature are changing? Okay, for those situations, then, we have something known as the combined gas law. And the combined gas law is, as the name implies, a combination of two gas laws. And those gas laws are Boyle's law and Charles' law. If we were to combine the two into one, we would end up with this: P1 over V1, which gives us Boyle's law, over T1 equals P2 over V2, P2 times V2 over T2. And this right here is the equation for the combined gas law. Okay, again, to be used when both pressure, volume, and temperature are changing. Okay, if we look at an example of how this works, here we can see that we have a gas that is at 110 kilopascals and 303 Kelvin, filling a flexible container with an initial volume of 2 liters. If the temperature is raised to 353 Kelvin and the pressure is increased to 440 kilopascals, what is the new volume? Okay, when I look at this problem, I should notice that I am given kilopascals, which is a unit of pressure. I'm given Kelvin, which is a unit of temperature, and liters, which is a unit of volume. So right off the bat, I should recognize that I am working with all three of those variables, and therefore this must be a combined gas law problem. Okay, we're going to start just like we did with our other gas laws and list our given information. Our initial pressure we set is 110 kilopascals. Our initial volume is 2 liters. Our initial temperature is 303 Kelvin. In the second half of the problem, then, we talk about how our new temperature is 353 Kelvin. New pressure is 440 kPa, and we are looking for the new volume. Okay, we're going to set up our equation. P1 V1 over T1 is equal to P2 V2 over T2, and when I plug in the numbers, I end up with this: 110 times 2 over 303 is equal to 440 times V2, that's my unknown, over 353. Now, just like when we worked with Charles' law, the easiest way to solve this is to cross multiply. And when I set this up, then, I end up with 110 times 2 times 353 is equal to 440 times, I'll rewrite this in a minute, 303 times x, okay, my unknown. Okay, so I'm going to go ahead and rewrite this and just make a little more room here. So again, going back to it, I have 110 times 2 times 353 equals 440 times 303 times x. When I go to plug this into my calculator now, I'm going to take 110 times 2 times 353 and end up with 77,660. I'm going to set that equal to 440 times 303 times x, which gives me this. And to isolate my x value, I'm going to divide both sides. Okay, my last step then is to divide. And when I do, I end up with x equaling about 0.58. Okay, my units here are going to be liters because that is what the units of my first pressure were. Okay, so once again, the combined gas law is useful when we're dealing with a situation in which pressure, volume, and temperature are all changing.